Okay, good. So the last talk is about modular optimization-based round-off error analysis of floating point programs. So this is work by Rosa, Abbasi, Boroujeni, and Eva Darulova. And Rosa is going to give the talk. Thank you.
So, hello everyone. I'm going to talk about modular round-off error analysis of procedural floating point programs. Suppose we have a complex number a plus bi, where a and b are real values, and we want to compute the radius of this complex number. So the formula looks like this, and it has many applications in geographical allocation, secret analysis, and so on. Computing the same expression in a computer in reals is not feasible, or if it were, it would have been very expensive. And so the same expression in a computer looks like a function like this one when we are using double precision floating point arithmetic. And the floating point arithmetic uses finite number of bits, and that introduces round-off error. And the round-off errors are the distance between the real value and the floating point presentation. So these errors possibly and most probably make the results incorrect, and at the same time, floating point arithmetic is used in critical systems, and we would want verified tools and rigorous correctness guarantees for such systems. So that is why we need to provide guarantees for the upper bound of round-off errors. So I'm going to first introduce some notation and the running example for our talk, and then continue. So we use the tilde symbol to represent floating point operations and values. And so suppose we have a real valued specification of function f and its floating point implementation, where the input parameters have input intervals and also initial errors. So our goal is to compute the round-off error, which means maximizing the difference between the real value and the floating point counterpart. And the main challenge is how to compute accurate bounds. Computing the exact difference is not feasible, or is only feasible for smaller computations, and so we need to over-approximate the results. On the other hand, this formula as it is too complex to reason about, because it's a combination of two theories. So it's a combination of the floating point and the real theories. And for example, we cannot just rephrase it as a SMT query, and since solvers have little to no support for combination of these two theories. So this is what we are after, and it's too complex. One approach is implemented in the FP Taylor tool. So assuming the rounding mode to nearest from the IEEE standard 754 for the floating point arithmetic, then this rounding model holds for floating point values, variables, constants, and operations, where epsilon bounds the relative error E and delta bounds the absolute error for the normals D. So we apply this rounding model on the floating point abstraction of f, floating point function of f, and we abstract it into the real value function of f hat. So now our computation is entirely real valued, but it's still too complex for optimization tools to handle. And FP Taylor, to reduce this complexity, applies Taylor expansion on the floating point abstraction of function f. So this is the first order Taylor approximation, and it allows one to approximate a sufficiently an arbitrary sufficiently smooth function with a polynomial term. Taylor series defines infinite expansions. However, if we choose a suitable point R to compute the approximation around, and then we can these terms we get a finite number of terms that are error terms in our case, and they include the first order derivatives and a remainder term that bounds the rest of the error terms, and for our case, or bounds the other higher order terms in general. So we apply the Taylor expansion on the floating point abstraction of our function f around point y, z, 0, and 0, and we get this. So there are the first order derivatives, and we also have a remainder term that bounds the error. And please note that since we are setting the e's and the d's to 0, then it means that we don't have errors, and so this f hat equals to f of y and z. So we have a concrete way of computing the an upper bound for the error by maximizing this expression over a given domain. In short, FP Taylor first computes the abstraction of function f, and then it computes the derivative symbolically. It then evaluates the above expression or maximizes the above expression using rigorous optimization techniques such as interval arithmetic and branch and bound. So we can say that FP Taylor computes the error in 2 steps, an abstraction or simplification step and a solving or optimization step. FP Taylor has support for transcendental functions, but they have well-defined derivatives. However, it does not have support for procedure calls modularity, meaning that we need to inline these procedure calls before applying FP Taylor, which means we will have very large expressions and large analysis time, as we have observed in our evaluation. So we have proposed a sound modular round-off error analysis for non-recursive procedure calls without conditionals, procedure code without conditionals. Our approach combines modularity and abstraction when analyzing procedure calls. And we have implemented our approach in a prototype tool called Hugo. And finally, we have an empirical evaluation of the accuracy performance of our analysis. Next, I'm going to explain our modular approach. So, in our modular round-off error analysis, we have extended the FP Taylor approach to also support procedure calls. Let's assume that this is the same example as before, and now it has been rephrased to have function calls. We can see that G is called twice here with different arguments that both have different intervals, and both of them are within the allowed range of G. For the simple case, now we assume that we don't have any input errors, and our analysis computes the error in 2 steps. The first step is the abstraction step, where we compute error specifications for each procedure of the program, and we use its interval for computing the error specification. Error specification is a function of the input intervals of the procedure. So here, beta of G is the error specification of G, and beta of F is the error specification of F. And we reuse beta of G in computing beta of F only symbolically at this point. So, and the step 2 of our analysis is the instantiation step, where we instantiate the error specifications that are pre-computed now with the suitable context and at the call sites. So, our goal is here in producing the error specification is that how to produce them such that they are abstract enough to provide an improvement in the performance, and on the other hand, they are not too abstract that we lose too much accuracy. One naive approach is to just compute a concrete error bound for each procedure. However, it loses too much accuracy. At the other hand, just pre-computing the derivatives does not lose accuracy. However, then we would have a modest performance. So we would want something in between. So in step 1 of our analysis, we extend the rounding model from before to also handle procedure calls. So for G, the abstraction is as before because it doesn't have any procedure calls, and for F, we treat the beta of G as a symbolic variable. We treat the the procedure call of G as symbolic variable. So we abstract G with a real valued result and an absolute error as the round-off error. Note that this round-off error, its value depends on the input variable of f. So it depends on y. So, I should point out that we do not need the concrete error specifications at this point for, of G at this point when we are computing the error specification of f. So again, we proceed as before with applying the Taylor expansion for G's as before. And for f, we apply the beta of G's as similar to the e's and the d's and as symbolic variables. So we would have first order derivatives with respect to the betas. Already at this point, we try to improve the performance by abstracting those smaller terms that do not affect the accuracy much. However, they would improve the performance if we evaluated them now, and then we wouldn't need to reevaluate them repeatedly at the instantiation time. And specifically, we are evaluating the first order derivatives with respect to the normal errors and also the remainder terms that do not have any beta terms themselves. So in step 2 of our analysis, which is the instantiation step, we instantiate each error specification of each function recursively using its input domain. So for here for beta of f, when we are instantiating the error specifications of G in it, then we use the input intervals of f. So we also check that before instantiating these procedure calls, we check that the input interval of the input parameters of these called procedures encloses the input interval of the arguments of these because we are using them. And so as I mentioned before, we have a trade-off here since we are pre-computing some smaller terms. We improve the performance. However, since we are potentially using wider ranges for evaluation, then we lose a bit of accuracy. As for correctness, so if we inline the beta of G's in the beta of f, then we would get the same round-off error formula that we would get if we had inlined all the procedures in f and then computed the error specification. So now let's assume that we have input errors. I will just give you a high-level idea, and the paper has more details. We use the triangle inequality and split the error into computing the propagation error, which is the error resulting from the initial errors, and a round-off error, which is the error resulting from the arithmetic computations. So we compute the error specifications in two parts. A propagation error specification, which is the gamma function here, and a round-off error specification, which is the beta function. And so for our example, the gamma of G is the propagation error specification of G, and the gamma of f is the propagation error specification of f. So to compute the propagation error specification, we again apply the Taylor approximation, however, this time with respect to the input parameters. So we implemented our approach in a prototype tool called Hugo. Hugo is on top of Daisy. Daisy is an existing round-off error analysis tool. And we have chosen two case studies to evaluate Hugo over them. We chose this case study because we expect the modular analysis to be more beneficial in these settings. Each case study has several procedure calls, and also some procedures may be treated as library functions that are called in other procedures. And each procedure also contains arithmetic operations and computations, and it potentially has procedure calls, and also a precondition that describes the allowed ranges for that procedure. So we have two case studies, one with matrix operations and the other with computations over complex numbers. And also the XL and the XS version of those two case studies have a smaller, have fewer or more procedures. Meaning that, we added these case studies so that we could evaluate the scalability of Hugo. So we compared, as part of our evaluation, we compared Hugo with two of the state-of-the-art tools, FBTailor and DAISY. We chose FBTailor because it implements the baseline symbolic approximation, Taylor expansion technique, and it has been shown to outperform the other tools. And we chose DAISY since DAISY implements a different type of analysis. It's a data based on data flow analysis, and it has been shown to be generally less accurate. However, then it is a bit faster. It's often faster. So. And we compare Hugo with these tools. And since neither DAISY nor FBTailor supports procedure calls, we inline the procedures before running DAISY and FBTailor. And similar to Hugo, when we are reporting the runtimes, we report the runtimes of producing errors for all the procedures of one case study. So, and these are our results. Hugo is faster for all the case studies except the complex XS case study, and it's often significantly faster. And this is with computing errors that are often within the order of magnitude of the errors that DAISY and FBTailor generate. And FBTailor is not able to compute round-off errors for two of the largest procedures of the complex case study that have a lot of procedure calls. But Hugo is even able to produce error bounds that are tighter than DAISY. And this is due to DAISY using a different type of analysis that is known to be less accurate. As for the complex XS benchmark, we expect this result that Hugo is slower. And this is due to the fact that our analysis has an implementation overhead that makes it more useful when we have a lot of procedure calls and a lot of code reviews. So to conclude, we have shown how to extend the optimization round-off error analysis approach with support with procedure calls, and in our evaluation, we have shown an interesting trade-off between the performance and accuracy, and we have shown that our analysis is able to produce shorter runtimes. Our tool accepts on purely procedural code at the moment. However, we expect our approach to be used in existing modular verification tools. And finally, Hugo is available. It's open source and it's online. You can try it if you want to take a look.
Okay, we will now move to questions. Okay, in here.
Nice talk. Is it working? Okay. Nice talk. Thank you. And I was wondering, you had as a restriction that you only consider straight line code. Would it be difficult to extend it to at least conditionals, which might be interesting, I guess?
Yes, that's an interesting question. Our goal was to just apply our approach on this current optimization-based approach and see how it works. But we did not aim for a fully a tool that supports all the features of all these features, and we think that this handling conditionals is another open research question, so we didn't.
Okay. Any other question? So I do have one. The use of expansion with Taylor series reminded me a little bit of a rather old tool which was called Fluctuate, done by Mathieu Martel, Eric Goubot, Sylvie Buteau, except that they were not really quite using the Taylor expansion itself. They were more like using a bunch of coefficients which were essentially related to imprecision on each input of a program. And I was wondering whether you looked, at least from the formal point of view, how it compares. I'm not sure the tool is still easy to find around, but the approach seemed a little bit like both related but different, because you are using the Taylor expansion and they are not quite doing so.
We did not compare with Fluctuate, but so I don't know. But I don't think they handle procedure calls, though.
No.
Yeah.
I mean, I believe it's also fairly old tool. I'm not sure it's still available at this point. Yeah. Any other question? I'm checking online too. So, yeah, there is one here.
Maybe I missed it. Can you repeat what you're actually doing with the arguments to your function? So you mentioned that you might have multiple ranges for the same procedure, and so what do you actually do with them? Do you union them, or so do you analyze just for one?
No. So when a procedure is called, then it's called with the parameters of the calling procedure. And then those input parameters, the input intervals for these parameters should be enclosed by the input ranges of the called procedure, so that we could actually use the abstraction that we pre-evaluated the smaller terms in the first step.
Okay, thanks.
Okay, so if there is no other question, I propose to thank again Rosa and close the session.